this is basically a classification example. So where I was pre-training an LLM, a GPT model in previous projects, and then I was loading the pre-trained weights from OpenAI. And then I was just adopting it for text classification, like an introduction to classification, because it's something I find interesting because most people don't know that you can adopt an LLM. It could be a BERT model, a GPT model, Llama model, to do simple classification, like you're familiar with usually from classic machine learning, like scikit-learn, when you train classifiers. So in this notebook here, yeah, it's the whole thing. I mean, of course, it's very verbose because we are also loading and pre-training the data. Actually,
And could you also
can
just
also.
increase your text
Oh
size?
yeah,
Just
yeah. Sorry.
no, that's cool.
Mhm. Yeah. So this is actually a studio interface. That's usually what I use for my coding. So it's because I can do all that stuff on a CPU, and then when I need my GPU, I can switch to the GPU here. Um,
Awesome.
and so basically in this notebook, I'm going from pre-training, so preparing the data set to loading the weights from OpenAI, and then modifying the architecture, and then basically, yeah, fine-tuning it. So it might take a few minutes because a lot of people are using the GPU. So let me use this one that I ran actually before, but let me clear all the outputs and restart. And then we can go through it step by step. So there are some packages I use. Actually, there are not too many. There are some dependencies. So there is a tick token. It's for tokenizing the text, which is quite fast. So you can use the Hugging Face tokenizers, for example, but I did some benchmarks. The tick token one is really nice. It's based on Rust, so it's pretty fast. TensorFlow, because most people probably don't know, but the OpenAI weights for GPT were in TensorFlow back then. And pandas for the data loading, because it's still relevant. We talked about pandas earlier in the good old days, but it's still relevant, I think, in the new days.
Oh,
Although a lot of people like polars too. Yeah.
yeah. I also just wanted to mention, like, if you
Mhm.
ask ChatGPT to generate a list of something for you and then put it in a spreadsheet, or there are lots of things.
Mhm.
If you ask, show me the code, most of the time we'll be using pandas as well, right? So,
Mhm. Yeah, yeah. And so here I have a data set basically. I use a very simple data set. It's text messages, not email messages, although email messages also exist because I wanted to keep it fast so that you can run it, that we can run it here in 30 seconds on a
mhm.
GPU or at home like in 10 minutes on a computer or like laptop. But yeah, it's a simple data set where we have ham, which means not spam, and spam messages. So we want to train a model that can classify those, an LLM basically. We want to repurpose an LLM to classify those. So in this case, it's not a balanced data set. It's also something to check, but to make the problem simpler, I balance the data set myself so that we have the same number of spam and ham. So the accuracy we compute is more meaningful. Otherwise, we would have to do F1 scores, precision and recall. And this would be another topic almost in balanced data. Then let's convert these hams to or spams to integer labels, do a random split. So I'm just browsing over that because that's not the interesting part. It's just the necessary data preparation part where we are creating a data set in PyTorch and um, loading or preparing the data loaders here. So these are just, regular PyTorch data loaders. So really, I'm skipping over it because that's not the LLM part. And I guess the audience is more interested in the LLM part. But the takeaway here is that we have a training set, a validation set, and a test set, and 130 training batches, 19 validation batches, and 30 test batches. It's like almost like a classic problem you would have in scikit-learn when you train a classifier, like logistic regression classifier or naive Bayes or random forest or support vector machine. Now comes the interesting part, the model, basically. So here we are loading the smallest model, but you can change that. You can change it to the larger models, the 500 million or 1,000, 1,500 million size model. And yeah, some settings, the vocabulary size, context length that we just talked about. If you want to use dropout, and if you want to use the bias units in the QKV matrices. So these are the QK query key and value matrices in the attention mechanism. An interesting side note is that back then the GPT had the bias units. So we are matching it because we want to load the pre-trained weights. But if you look at newer architectures, bias units are not really necessary. I think like all the new models, they don't really use bias units anymore. But yeah, if you're interested, you could actually also take the larger model here and put it in here and train the larger model. So you can see they are actually all the same, except they repeat the number of layers different number of times. So, and layers here refers to the transformer blocks and then the attention heads. So these are just slight variations, but ultimately the architecture is the same for all these models. So this code, the notebook should work with all the models sizes here listed here. And I'm not showing you the model itself. I'm just importing it here because it's quite verbose, and this would be another, I would say, podcast or tutorial, but it's all contained in in this big file where I have the architecture implementation. This would be somewhere down here, the GPT model, which in turn has transformer blocks, and the transformer block in turn has the attention mechanism, and also the should be here the feed forward module, which in turn looks like this. So it's kind of like rabbits all, or how do you say, the rabbits all the way down, or the saying, but it's like very recursive almost. You have a lot of things going on here. Yeah. Okay, so here we are loading the GPT model weights. And for that, I also have abstracted this away in this one here. So the original weights were in TensorFlow. So I have written a utility function that converts it to PyTorch basically. So it's not very interesting. It's really like loading the parameters from a TensorFlow checkpoint and returning them as tensors. And then that's what's feeding into the model. So basically, I have a function that downloads the weights and then initializes the model that is contained here, and loading the weights into that model. And did I execute this? Yeah, I did. You can see the check mark here. And then now before we actually do anything with this model, let's actually make sure it works before we fine tune anything. I think this is what we talked about before. It's like the sanity check. Can it generate, coherent text? So when I execute this, I hope that it can generate coherent text. And you can see, so the input text is every effort moves you. And then the output is forward. So it's the first word is it's completing the sentence because it's a model has been pre-trained. So it's like what it does, it's trying to complete the input, the next token prediction. And then you can see it generates one more sentence. I kind of kept it here. You can, you can increase this and it will generate more text. But yeah, so but see, it's also kind of repetitive because the thing is with this model, it's a very small model. It's not the best model yet, right? So you would instruction fine tune it later. And you can see also the larger models, we can change it maybe later if we have time, but they would perform a bit better. So, but the point is really it can generate coherent text. If you make a mistake in your implementation, you would notice it's just generating gibberish. It wouldn't be able to make any sentence that has a grammatically correct meaning, basically. Now comes the interesting part. Also, we can actually look at the architecture here. So what you can see here is the GPT model architecture. So it consists of the token embedding. So we are embedding the input text. And we have a vocabulary size of 50,000 words approximately. It's embedding each token into a 768-dimensional vector. And we have also positional embeddings that are the same dimensions. They are just added to each other. Optional dropout, we don't use dropout here, so it's 0. And then the transformer blocks, which consist of multi-head attention, which in turn consists of the query, key, and value matrices, a projection layer, the feed forward module, which is really like a multi-layer perceptron, layer norms. So here it looks like they are applied next to each other, but that's just how it's sorted here alphabetically. But they are actually not applied after each other. They are in different positions if you look here in this file. And then really the GPT architecture is just really repeating this transformer block. So you have it the first instance, the second instance, and the third instance, and then it's dotted out here. I think you can click here, and then it would show you all the ones up to 12. So Python uses 0 indexing, so it would be the 12th transformer block. And that's essentially it. And then you have like one output layer that takes each token and projects it back into the vocabulary dimension. So you can then convert using the tokenizer in an inverted way. You can convert the token IDs back into the text. And so this is the architecture. But if we are interested in just classifying text, let's say spam and ham, we don't need the whole vocabulary as output. So we just need an answer. Is it spam or not spam? So what we could do is we could actually replace this layer here by a layer that only has 2 output units. Actually, you can go even further and have 1 output unit, like in binary classification. But to keep it more general, we set it equal to the number of classes, which is 2 in this case. So what I'm doing here is first, I'm freezing the whole model that all the parameters are not trainable. And then I chop off this last head here, the output head, the classic. So here in this case, it would map to the vocabulary. And I replace it by my own layer. So this is a new linear layer initialized from random weights, and it has 2 classes for spam and not spam. So in this case, I'm replacing the last layer. And in addition, you don't have to do it, but usually it performs better. I make the last transformer block and layer norm also trainable. So basically what I'm saying is I'm freezing the whole model except for this final part here and then the final layer norm. So this one. So now after this modification, this one is trainable. And this whole transformer block here, that includes the feed forward, would be trainable. But all the other ones, they are just frozen. I don't need to worry about them because they're actually quite good at extracting language or, working with language. And let's then train such a model. So first, what we could also do is actually, we can try it on some text. This is just showing you after the modification what the output looks like. So if I have text 1, 2, 3, 4, 5, 6 tokens, so the dot is a separate token. Now before, what the model was doing, it was outputting 6 output tokens, but each token had 50,000 dimensions, like the vocabulary. But here's just a sanity check. After our modification, each token has 2 output dimensions. So this is similar to deep learning when you train a, let's say, convolutional network to predict 2 classes, like whether something is a cat or a dog, where the first column would stand for, let's say, cat, and the second one would stand for dog. And here it would be not spam and spam. So you have 2 columns as output. And for that, we would maybe need to know a bit more about how attention mechanisms work, but they are mapping from one token to the other, the attention scores. And then the output are these vectors. So the first output vector has information about the first token. And the second vector has information about the first and the second token because we have this causal attention mask. And the third output vector has information about the first, second, and third token. And then the last vector here, it has information about all the previous tokens. So in this simple example, this would be these 6 tokens. So all the information about these tokens multiplied by the attention weights would be contained in this output embedding. So what we are doing now is we are only focusing on the last one because it has information about all the words. If we focused on this one, it would only know about the first word. And so this one is really the most, I would say, information rich. So what we do now is we just focus on this last output token, and that is the one, the last output token that we fine tune. So what we can do then is a small utility function to compute the loss, but the loss is only computed about for the last output token here. And this is like, just the regular, like cross entropy loss we would use in PyTorch for training classifiers and so forth, but only focusing on the last output token. And then we have, so this is doing it for one batch. And then we do the same thing for the whole data loader. So earlier we said, if I scroll up again, I hope it's not too much scrolling and people don't get nauseous here. But when we go up, we had 130 training batches. So this loader function will just compute the loss over these 130 training batches, basically. Okay. I mean, we already reached the bottom. So I think the most complicated stuff is already past us. So right now it's the fun part where we get to fine tune. So this is the loss loader. And then we have the same thing we apply it here. And that's one thing, that always gets me in PyTorch. I always forget when I just want to check something. I forget to use the no grad context or inference mode. If you don't do that, it will compute or construct the computation graph for all your iterations because it's thinking you're training. And this one disables that so we don't, blow up the memory here. Okay, let's just execute that. So this just gives us the initial loss before we start training. So it's around 3. Loss is usually not super interpretable. So loss is, almost like a not super meaningful value. So we do the same thing for the accuracy. So we have an accuracy loader, and we can apply that to the data set here. And we can see, just as a sanity check, that our model, before we start training, only gets roughly 46, let's say 50% accuracy. So it's really not very good at predicting spam and ham. It's just like to make sure this is our baseline, and let's see how good we can get when we fine tune it. So here I have a very simple function. It's really just what you would use for training any convolutional network classifier or even logistic regression in PyTorch. So here it's it's iterating over the epochs, putting the model into training mode. Usually best practice to zero out your gradients from the previous iteration because, there are tricks like gradient accumulation, which is why this exists, but we don't need that here. We calculate the loss. And then here's our backpropagation that we talked about earlier. So we just do dot backward to calculate the gradients, update the model parameters, and the rest is really just here. This is just, tracking things, printing things to the command line. But really the fun part really happens here in these 3 lines of code, basically. Calculating the loss, backpropagating, and then applying the updates, basically. Let's execute that. And then, one more thing. I have an evaluation function. I think I'm using it somewhere here. Well, maybe not. The evaluate model function. I think I was using it somewhere here, which is why I defined it. Here we go. So I'm using this evaluate model function, which will it's just a wrapper function to compute the loss for all the borders here in one line. So it's really just computing the loss. And then let's actually execute that. So this is essentially just a time function, initializing the optimizer, 5 epochs, and then feeding the model and the data loaders, optimizer, and so forth into this train function that we just defined. And let's see what happens. We have not defined that one. Yep, let's do that. Yeah, and then it's training. It should only take like 20 seconds because we are running this on a GPU here. So you can see it starts out after one epoch with 55% or if 75%.
We're already above baseline.
Here. Yeah,
that's great.
A little hiccup here, but it's improving again.
75%
in 27 minutes. So also I should say this is only approximated. So here what we did is we only computed it over 10 batches just to make the evaluation faster. So we can also then evaluate it on the full case. So here, let's see. Yep. So after one epoch, it kind of like saturated here already. So doesn't really do much. Let's see the.
Yeah.
Okay,
so
it could actually. It's not great, but it could be improved still. But it is definitely better than the baseline here, right? It's overfitting a little bit. And let's compute the training, validation, and test accuracies here. Okay, it's 80%. I was actually, maybe I have the wrong file or the wrong hyperparameters. I was actually getting 95% earlier this weekend when you check out that GitHub notebook. Maybe let's run this from the top. It could be that I ran something twice.
And while you're running that, there is a question from Komal. Komal asks, do we feed forward the data set until the last attention head and train the params on last attention head and linear layer?
It goes through all the attention heads and then they get combined usually. So it's a good question. So if we look at the code here, we have the transformer block, which is here, and it uses the attention mechanism. And let's scroll up. So this is the attention mechanism here. And we have yeah, we have the reshaping here where we are reshaping it to the number of heads times the head dimension. So we are basically collapsing so we are collapsing the dimension over the multiple heads. So it's all the heads concatenated to each other, basically.
Right.
If that makes sense. So
Yep.
in that sense, it's not necessarily the last head, it's all the heads. But if the question was about which multi-head attention module, then yeah, we are going through the whole LLM up till to the last one. So where we had, let me see. Oh, see, now we got the better accuracy. I must have run something twice before where, so now we get the really good one where we have 95% test accuracy. Yeah, so, but the question, going back here. One more, yeah, here we are. So it's really going through the whole model, through all the 12 attention blocks or multi-head attention blocks in the transformer blocks up to the last one. And then it's really, yeah, getting the last token from here, from that layer. But everything else, it uses the full thing. So it's not just the last one, it's using the full thing. And then from the output layer, we replace that. We replace that with the one here that has two output classes. But it still outputs, so the model, the attention mechanism still outputs. If you have 6 input tokens, it always also outputs 6 output tokens. So we are only focusing on the last output token.
Makes sense. Well, thank you for that wonderful enlightening demo. And I've added the link to the GitHub notebook in the chat, and I'll do so in the show notes, but we'll also include this stuff when we
I think yeah. So this is yeah, we can see it now works. It is actually converging, and you could technically, if you're interested, you could change the model to a bigger one, right? I mean, just briefly, let's scroll up. Okay, I don't want to take too much of everyone's time, but yeah, this is if someone wants to see how, I mean, in this case, I think you probably won't do much better because it's a relatively simple task, but you could technically use one, let's say this model here, plug it in here. And okay, one little change, oops, I forgot the closing parenthesis. And one little thing you have to keep in mind though is if you do that, okay, I probably need to restart this because part of the model is initialized already. Sorry. Okay, maybe this is too much for this podcast because I don't want to take too much of your time, but maybe just, yeah.
Oh, I was going to say, while this is executing, I did have another question, but you can.
Okay.
Well, yeah, my question was, when talking about the full LLM lifecycle, we did talk about deploying and monitoring. We didn't talk about evaluation at all. And of course, this is a classification problem where it's very easy to define accuracy and these types of things. And I feel a bit cheating tagging a question like this on near the end of an episode because I think evaluation needs a whole series of podcasts itself. But I'm just wondering if there's any advice you could give people thinking through how to evaluate LLMs and this type of stuff.
Yeah, I think the challenge nowadays, the biggest challenge with evaluating LLMs is making sure we use an independent test data set or like questions for evaluation. So to evaluate an instruction fine-tuned LLM, there are multiple benchmarks. There usually a lot of them are Q&A based. So basically, you have an instruction like answer, so multiple choice, pick one of these answers or answer in a single word, like what is the historic date when so and so happened, and then if it outputs the correct date, then it's correct. And the problem though with that is most of the benchmark data has probably been used for pre-training the LLM. So if you evaluate an LLM really for your own application, I think I personally would make sure to include some data that has not been used for pre-training. Also interesting is, for example, if you develop your own system where you just want to make sure the LLM learns well when you do continued pre-training or instruction fine-tuning. Personally, it's just like a trick, but what you can do is you can change the facts in your data. So for example, you have your pre-training data, and if you feel like, okay, this is something general that could have been used in the pre-training, you can just change the fact in that. So you can change, like if you have a Wikipedia article with some historic dates, you can just change the historic dates in that article, for example, or names of people involved in that article, and see what the model outputs. Is it learning from the document you fed it, or is it like recalling it maybe from memory that has, so which gives you an indicator that it has already seen this article before if it recalls the original memory, basically, the original date. So like a little trick. Another big challenge is this is only checking factual correctness. It's not always sufficient, I would say. A lot of people, when they're building chatbots, they care about conversational tasks. And this is more tricky. I think most people, what they do really is looking as a LMSys chatbot arena where they are comparing two models side by side and then just saying, okay, this model is better than the other, like thumbs up types of responses. And then you can compute a ratio of how many people preferred one LLM over the other, more like a relative comparison. But you can also use, I've seen that a lot in papers recently because it's cheaper to use GPT-4 to judge two answers, basically. It's like more to make sure does the LLM output coherent text, grammatically correct text. So, but it is an open problem still. So yeah, not an easy one. So just briefly, like we downloaded the bigger model now. And if you want to use it here, should work now. Let's see if it also, let's see if it generates more, if it repeats itself less. Yeah, see, this is already better than the small model. It's not repeating itself so much. I mean, here it starts repeating itself, but yeah. The only difference you have to still be aware of now, the output dimensions is 2028. I think before it was smaller. So you do have to, when you add your layer here, you have to match this number. But other than that, yeah, you can now train a larger model, basically.
Very cool.
On the same data set. Yeah. And also, if people are interested, we do have this LitGPT open source library where we have implemented 20 or so LLMs that are not GPT. So this is the one that is really with best practices, multi-GPU training, where my implementation here is really like a GPT model, GPT focused, but here this is like a more general one, with Gemma, Llama 3 and so forth, LitGPT. So yeah, so if people are interested in from scratch training, I recommend checking out this, of course. But then like after that, I think LitGPT would be a good one because it's still relatively readable, all open source, and people can look at also how we implement LoRa and stuff like that. So yeah, it's a bit more code because it's made for efficiency and production purposes. But yeah, I hope people found that useful, and I like that stuff. It's a lot of fun for me. I realize maybe not fun for everyone, but I hope everyone, enjoyed the quick demo here.
I found it incredibly enlightening, and a lot of people in the chat seem to have as well. A lot of people have said thank you.